let's take a look at Major League Baseball players. So the population I'm interested in looking at here, 2019 Major League Baseball players. And that is a population, right? All the baseball players. They have an average salary. I want to know what it is. That's a parameter for that population. Now in StatKey, I have some of this data. So from the StatKey website, I'm going to check out sampling distribution for a mean. Couple goals here just to go over what's the difference between a sample and a sampling distribution, population and a sample, parameter, statistic, and how sample size matters. So I'm going to start off from this population. So StatKey has here all 877 baseball players and their salary in millions from 2019. That's my population. I'm going to take a sample of size 50 baseball players. To do that, I set the sample size here, and then I generate one sample. Here, my sample has a mean of 4.791 million. That sample is over here on the side. It looks kind of similar, just smaller than the original sample here. 50 players, average salary is 4.791 million. Now, something that's important about taking a sample is if somebody else made a random sample from this population to generate a new one, they're going to get a different set of numbers. So this new one right here, oh, that's mine, new one over here, it has a mean of 4.939. And if we generate another sample, so we randomly select 50 of the baseball players, we get a different mean. And every time we generate a new sample, we're going to get a different mean. Sometimes they could be extremely different. So, and it's not improbable, right? Most of the players live down here in the smaller salaries below, right? What's the median here? Median is 1.4. So half of this 877 group of players, half of them make 1.4 million or less. The average is 4.15 million. So more than half of them make less than 4.51 million because of the skewness of this data. And the idea of sampling variability means that every sample is different, right? Every time we generate a new sample, it's different than the last one. You're unlikely to get the same sample twice in a row. And even though these are stacked on top of each other, each one is different by a little bit. It's not the same set of players. So I'm just going to pick one of these. I'm going to go back to, what was that first one I had? Over here somewhere. It's that one, I think, 4.791. I'm going to go with that sample. When I click one of these points here, it puts the data in this sample area, and I can go grab the data table. So I'm just going to grab this table. In order to copy and paste this, I can't grab the name and salary at the top, but I can grab the first person's name by clicking just on top of that letter R there, dragging over and down. Now, if you do this too, you're going to get a different sample of 50 people than me, and that's cool. That's the way it should be. Control C, copy that. And I'm going to go to a new StatKey page, StatKey, just search for it. And then now I'm going to look at the confidence interval page, so different page than before. And here I'm going to replace their data by going to Edit Data and put the data I copied in. Before I continue, I just want to double check these checkboxes. First column is identifier. Yep, I do have a first column identifying those numbers. Check. But I did not, if you remember, copy the header at the top, that thing that said name and salary. So I'm going to uncheck that one. It's important you get that right when you put your data in here. Otherwise, you'll end up with errors or StatKey might just freak out on you. Now, you could try this along with me if you want, or you could just watch, check it out. So here's a zoomed in histogram dot plot of my data. And that data right there is this data down here. It's just that scale is much higher there. So if we look, now here we have hundreds of players, right? So there's like almost 500 players that make from, what is it, like 500,000 to almost 2 million in this first column here. And in my column here, I only have a few players that make around 500,000. And that is this first column here. Okay, so it's just graphed a little bit differently, but there's my 50 players. So this is a sample. My sample has a mean of 4.791. I want to write that down. So now I have a sample. I took a random sample of 50 players. I just took one of those random samples. And I have a statistic. A statistic is a calculation you make based on a sample. And so my statistic is X bar, the mean, and it's 4.791. Now, rarely do we actually know the whole population. Usually it's this big group out there that we don't have access to everybody, but here we do. The average salary here, since it's a population, would be given the letter mu, and it is, I think, 4.51. Let's go back and look. Yeah, 4.51 million is the actual average of this population of baseball players. 4.791 is the average of my sample of 50 baseball players. So any situation where we're analyzing, trying to make a prediction, we need to know a few things. What is the actual population we're concerned about? And what parameter about that population do we want to measure? Then we take a sample and calculate a statistic on that sample to estimate the population parameter. So we now have an estimate, right? So I could state based on the data so far is we believe the average salary of Major League Baseball players in 2019 is $4.791 million. Right? So in general, we don't know the population. All we can do is guess at it with a sample. And this is my guess based on the sample. So somebody might say, well, did you really get information about every baseball player? I said, no, I took a random sample. I think it's representative. So this is a good estimate. So then they might say, well, how good is your estimate? Oh, okay. To see how good an estimate is, we have to calculate a margin of error. To calculate a margin of error, we need a sampling distribution. So what is a sampling distribution? A sampling distribution is when you go take a whole bunch of different samples, all of size 50, and record the mean of every sample. And you do that thousands of times. So now I have, let's go with 6,000, 12. So I went out and grabbed 6,012 different samples, each of 50 different baseball players, and all I'm plotting here is the average. So I just get 50 players randomly, calculate the average, plot the point. And I just had the computer repeat that for me 6,112 times. And I get this distribution right here. Notice the mean, the middle of this distribution. Distribution is just this graph, is a distribution, 4.495. That's always going to be pretty close to the population. So the sampling distribution for population will hover with a center about the mean of the population. Now, generally, we don't know the whole population, so this information is not known to us. So over here, I have the sample to do that with. So now what I'm going to do is I'm going to resample based on the original sample. What that means is I'm going to choose 50 players based on these 50 players. And it's like I have a deck of cards, each person has a card, and I look at the card, write down the person and the salary, I put it back in the deck, I shuffle it. I look at the card, I write down the person and the salary, and I put it back in the deck. I do that 50 times. That gives me a new sample. It's not going to be exactly the same as the original because I might pick somebody more than once, and I can do that again. And so I get another new sample, and another, and another. So the new samples are appearing down here. So if you watch this bottom right corner, you'll see that every new sample is a little bit different than the one above. Sometimes they're almost indistinguishable, but they're similar, right? We have this big stack in the middle. We're almost always going to have a big stack, in the beginning over here, matching the big stack over there. There's very few baseball players in this sample that make a lot. There's one that made 25 million, one made 26 million. So sometimes they reappear, but they're not always going to. So to build a sampling distribution, I just keep doing that thousands of times. So instead of one at a time, and again, what's each of these dots? It's an average of a resampled 50 people from this group. Resample 1,000 times, resample another 1,000, and another, and another, and another, and another. It should look similar to the population distribution. There's a couple of differences though. The first big difference is that because we're sampling from this sample, the means aren't going to stray too far from that because this is what I have to work with here. So the sampling distribution based on a sample is going to have a similar middle to the original sample. So here my original sample has a mean of 4.791. My sampling distribution has a mean of 4.795. Close, not exactly the same. If I reset this and start over, a similar thing is going to happen. It's going to jump around a little at first. I got a real extreme one over there. And so here I have 4.8 versus 4.791. It's pretty close. And every time you do this, you're going to get a slightly different sampling distribution. But what I can do is I can use this sampling distribution now to try and get a margin of error to answer the question, how good is my estimate? So to do that, I hit the two-tail button here. And what StatKey does is says, okay, we're going to give you what's called a 95% confidence interval, which means we're going to put 95% of these averages in the middle. So that means there's going to be 2.5% to the left, 2.5% to the right. So it basically looks at all these points and counts, where do we get to the place where we have a point where there's 2.5% below that? And it says, oh, right here at the sample that had an average of 3.192. And it keeps counting across all these points in here. And it says, okay, let's collect another 95% of these points. So 95 plus 2.5. So it goes up to 97.5% of the points, these averages, and stops. It says, okay, at 6.619, we've now collected 97.5% of all of these averages. So that means the middle 95% has to be between 3.192 and 6.619. So I want to copy this and scribble on it a little bit to show you what it means. And let's do a new page. So this is a sampling distribution. What is a sampling distribution? In this case, it's a distribution of sample means. Okay, well, how many sample means are here? There's 7,000 sample means. How big was each sample? Each sample was 50 baseball players. That's what I have presented here. According to this, the point estimate here, and that's the estimate of the population parameter, I'm estimating that mu, the population average, is approximately 4.8 million. It could be as low as 3.192 million. So when I take these two lower and upper boundaries, lower, upper, that gives me an interval estimate instead of a point estimate. So this right here, that's my point estimate. My interval estimate interval in math is a parentheses, put the lower number, 3.192, comma, put the upper number, 6.619. So that's my interval. So I think that the average salary of a baseball player in 2019 was somewhere between 3.192 million and 6.619 million. To find the margin of error, we look at how wide this interval is and cut it in half. So margin of error is to just take the upper number minus the lower number, divide by 2. So that would be the 6.619 minus 3.192, cut it in half. So we get a calculator out for that. 6.619 minus 3.192, divide by 2. And my calculator says that it is about 1.7135. And sometimes they come out to be smaller numbers. It's centered here, shrink this down a little so we can reuse it. All right, so that's what I want right there. 17135. So my margin of error, 1.17135. So what does that mean? So going back to the point estimate here, it means I think the average is 4.8 million, but I could be off by about 1.17 million. So another way to state the interval estimate is to state the center, in this case x bar, plus or minus the margin of error. So I could say 4.8 million plus or minus about 1.17 million. So from the center to the edge, so this would be plus that 1.17 million, and from the center to the edge, that would be minus that 1.17 million. So that's how far off I am. And somebody will say, well, being off by 1 million, that's kind of a lot. And I could say, well, 1 million out of 5 million, I'm about 20% wiggle room on either side, and 20% is a little far. So I might be asked to reduce that margin of error. So there's two ways I could reduce it. I could say, well, let's just be less confident. Let's go for 80% confidence. So 80% would be a narrower middle section, but I'm less confident. So that kind of sucks. Otherwise, the only way to reduce the margin of error is to increase the sample size. So then I have to go out and select more. So let's do that. Let's see, I want to keep that one there. So let's grab it from here. Edit data. Ooh, interesting. I ditched all the names on me. Why did it do that? Doesn't matter. I just need the numbers. And I'm just going to make a new window because, oh, I deleted that too. Oops. Oh well. Just do it again. I want to compare the size, sample size of the 50 with something else. That's what I need. With me here. So I'm repasting in the data. I lost the names, but I got the numbers. I do have a first column identifier, and I have a header now. Okay. And this time, though, oh, I lied. I can't increase the sample size until I get a new sample. Back here. Okay, there we go. 200. This time I'm going to grab 200. Generate one. This time we get 5.109. I'm going to go grab that data. This is what I wanted. New sample, but a bigger one. New ones in here. And I have an identifier column, but I don't have a header row. Always double check those. So here I have 200 players randomly selected from the original 877 population. Previously, I had 50 players from there. Let's get this one up again. A little different than last time, but similar. And there's another 95% confidence interval. Notice it's similar but different than last time. And again, because of sampling variability, every time you run these simulations in StatKey, answers are going to be a little bit different than last time. And in the homework problems, I try to take that into account. It's a little challenging. So let's generate thousands of samples. And now notice, again, here I have 200 players in my sample. And what I want you to notice is when I get the middle 95%, now I'm 4.1 million to 6.1 million. Whereas before, with only 50 players, my spread was 3.1 to 6.6. So this is much wider than this one right here. And let's just double check that. Calculating the margin of error. And StatKey doesn't directly give us that. We have to do that subtraction I showed earlier. So this is again a sampling distribution. This time it's 6,000 samples, each of size 200. And I want to know what's the margin of error here. And so the margin of error in this case is going to be that 6.118 minus the 4.159. All right, so we just take that lower number away from the upper number and divide by 2. So put that in my calculator. 0.18 minus 4.159 divided by 2. And this time I get a smaller margin of error. I get 0.9795. So I have a smaller margin of error here. And that's because I have a larger sample size. So the moral here, sample size matters. A larger sample size leads to a smaller margin of error. Now, the problem is the cost of a larger sample. So at some point, you got to say, can we really afford to do a sample of 2,000 people? Or can we really afford to do a sample of 1,000? Or can we only afford a sample of size 100? So you have to balance cost, accessibility, with this idea of a margin of error. How close is your estimate? Another thing about these estimates here, I'm not guaranteed that the population value is going to be in here. It could be that I have a sample that just doesn't work. So if I go back to the original here, this is the original 877 players. And let's grab a sample that's, say, unusually low. And there, looking for a dot that comes out way down here. Lower, fine, we'll just go 100. There we go. So we're going to grab this one right here. So that one's pretty low compared to the average. So do I have that one down there? Yep. So if I grab this group of 200, so it is a random sample, but it might not be representative because the average is lower. And sometimes that makes sense. I mean, again, think about it. Half of the players made less than 1.4 million. But the mean was 4.5 million. We have that wicked skew right on this. Let's make a new stat key confidence interval for a mean. Drop our data in. So again, I have, let's see, first column identifier, no hetero. This time my average is 3.5, which we know is below, but is it significantly below the population? That's what we're going to test out here. So if I make a 95% confidence interval in this case, notice that the interval is from 2.8 million to 4.335 million. The actual population mean is out here, 4.5. It's not in my confidence interval. So this gets back to that idea of being 95% confident. What does that mean? So like for this one right here, I am 95% confident that the average baseball player salary or the average salary of all 13. Just one moment here. Hey, Alejandra, I'm in the middle of a recording. I'll be done in just a moment. So the average salary of all 2019 Major League Baseball players is between, this one says about 4.2 million and about 6.1 million. In this case, I happened to get the actual population mean, which is over there, but in reality, we never know that. In this other sample and distribution I made, I was estimating the average baseball player salary was between 2.8 million and 4.3 million, and I missed the average this time. So that gets to the idea of what does it mean to be 95% confident? So that's the confidence level. What does the confidence level mean? 95% confident. So it doesn't mean there's a 95% chance that I found the actual population mean. It doesn't mean that 95% of averages will be in that interval. It doesn't mean that 95% of baseball players will have salaries in that interval. It's confidence in the process. So that means 95% of similar samples will produce confidence intervals that actually contain the true mean. I don't know if mine is one of them. There's 5% of similar confidence intervals don't contain the true mean. And the answer is we just don't know. So this isn't a probability, it's a confidence in the process that we're using to make the prediction about the center and the spread, which is, again, how accurate we think our estimate is. All right, that's it for now.